Hello there. Now we have a question based on the Doppler effect, subtopic in waves. A car travels at a constant speed along a straight line PQ. A loudspeaker attached to the car emits sound of constant frequency F. The stationary observer is at point O. What does the observer hear as the car moves from P towards Q? Okay, so this is an interesting question where Doppler's effect is basically a situation where if an object emits a wave, for example here a sound wave, and it is either moving towards or receding us, then we will perceive as if the frequency changes, when in fact the frequency does not change, but due to the relative motion between the observer as well as the source of sound or the source of wave, then we will perceive as if there is a change in frequency. So what does the Doppler effect states? Basically, the observed frequency, which is the frequency observed by the observer, is given by a ratio with respect to the source frequency, when in fact the source frequency does not change. So in this case, if you have an object that is emitting sound approaching you, then you will as if perceive that it has a higher frequency. So in this case, you have Vs, where given that Vs is the speed of sound, which is roughly around 343 meter per second. So this is just a constant value. So this Vs is basically minus the velocity of the source that is moving. So there are two types of velocity here. One is the velocity of the sound wave. The other one is the velocity of, in this case, which is the car. So V is moving at a constant speed. So in a typical Doppler effect situation, if that object is moving towards you, then you will perceive as if it has a higher frequency. If it is moving at a constant speed, therefore that frequency will just be a constant frequency. However, in this case, notice that the object or the car is not moving directly towards the observer, but it is actually moving at a distance that is perpendicular to the observer, which is OQ. So we need to analyze this situation according to what we are facing with. Now, in order to do this, what we need to know, although V is constant, but V is constant from P to Q. What we want is actually the relative velocity moving towards P towards the observer O, from P towards the observer O. So in this case, what we need to do is actually to resolve the velocity. Now, if this velocity is constant from P to Q, but if you resolve it, this one you have to be very careful, because when you resolve any vector, that vector needs to be the hypotenuse. So when you resolve it, what would you get is basically the right hand triangle will be at this point of the vector. So here you will get, let's say for example, this is angle theta. So this angle, this vector, when you resolve the resultant constant V, you will get V cos theta. So you can assume that, for example, this V is basically the constant speed of the car from P to Q. What we want is basically the relative velocity from P to O instead. Now, VPO is basically represented by this value, which is V cos theta, where the theta will change as the car moves from P to Q. Let's say, for example, in this case, in one instance, you have the car at P. If somewhere in between here, this theta, let's say for example, this one is theta 1 and this one is theta 2. Of course, theta 2 will be greater than theta 1. So that means the relative velocity from the car towards the observer will change, although the car is moving at a constant speed from P to Q. So we have to have some sort of an understanding of how this setup is actually presented to us. So we just simply substitute the constant speed v with the relative speed v cos theta here. Therefore, what we can get is basically Let me just write this down. The observed frequency is equals to Vs over Vs minus, we substitute V here, is equivalent to V cos theta, multiplied by Fs. Because just need to highlight again, this V is not just the constant V, but instead this should be V relative from P to O, not VPQ that is constant. Okay, now let's analyze the situation here. As theta, as the car moves from P to Q, what happens to theta? Theta increase. If theta increase, what happens to cosine theta? Now, some knowledge of trigonometry here will help. So here, let's say for example, if you have your angle theta, and this one would be your cos theta, you will know that cos theta is something shaped like this. So it started off with a very small theta, and the maximum theta that it can go will be basically theta max will be 90 degrees. So you are actually analyzing from 0 degrees to 90 degrees. So here you know that as theta increase from 0 to 90, cos theta will decrease from 1 to 0 in this case. So what happens when theta increases? When theta increases, cos theta will decrease from 0 to 1. So here what will happen? If you analyze this term, when theta increases, cos theta will decrease. When cos theta decrease, V cos theta will decrease. When V cos theta decrease, what happened to the denominator here? Vs here. Just write this down. Therefore, Vs minus V cos theta automatically will increase. That means the denominator increases, therefore the fraction will eventually decrease. That means Vs over Vs minus V cos theta, all of this fraction will decrease. Therefore, what will happen is the observer will perceive a higher frequency, but that higher frequency will decrease as the car moves from P to Q. Therefore, the answer would be a frequency that is more than F, but decreases as the car moves from P to Q. So the answer is C. Okay, so you just have to understand that theta here, this theta is basically the relative theta, theta 1 and theta 2 will increase as the car moves from P to Q. So when theta increases, cos theta will decrease from 1 to 0. And then what happens is that Vs minus V cos theta will increase. Therefore, when the denominator increase, the fraction will decrease. Therefore, it will causes that the frequency, the perceived frequency will decrease. Thank you.